Good afternoon, everyone. Welcome to Student Revision Tutorials. Today we are going to look at tech-active questions for mathematical methods focusing on the logarithmic and exponential functions. I am Shelley Cross, and I currently teach mathematics methods at St. Hilda's School. Let's look at our learning intentions for today. So in today's webinar, we will solve logarithmic equations on a calculator using 𝗬𝗪 and in a graph application by finding the points of intersection of two functions. We'll also solve exponential equations in a calculator application using 𝗬𝗪 or numerical solve, and in a graph application by finding the points of intersection of two functions. Very similar strategies for those two, both logarithmic and exponential functions. We'll look at a couple of transformations of logarithmic graphs and graph sketching, and then look at a modeling question involving logarithmic data. So here are our questions. Let's get started. So the calculator software that I'll be using today is the TI-Nspire CX Premium Teacher software. I will be starting with a calculator page. With a new document, I add a calculator. The question I'm going to solve for x is 2 natural log of x minus natural log of x minus 2 is equal to natural log of x plus 3. So using the numerical solve function, I hit Menu, Algebra, Numerical Solve, and type the function within the parentheses. So I have 2 times the natural log, so control natural log, x, right arrow to get out of the brackets, subtract control natural log of x minus 2, right arrow to get out of the brackets again, equals control natural log of x plus 3. Now I'm solving for x, so at this stage I need to put comma and specify the variable that I'm solving for. Enter, and I get my answer of 6. So that solution could have been done analytically, but can also be done on the calculator. To verify the solution, I would like to plot two graphs and find the point of intersection of the two graphs. The x-coordinate of the point of intersection from my numerical solve should also be 6. So Control Doc to add a graphs page. The first graph that I'm going to draw is the left-hand side of the equation. So it will be 2 control natural log of x, right arrow, minus control natural log of x minus 2. So the left-hand side of the equation looks like that. Second function that I'm going to enter will be the right-hand side of the equation. So hit the tab button to get the menu line back. And I'm looking at control natural log x plus 3. Enter. So these graphs intersect somewhere over here. I'm going to just change the domain that I can see the graphs for so that I can focus a little more on the right-hand side. So I'm going to change the minimum x value to -5. Double-clicking on that value, select it, and push Enter to rearrange the window. Now, I can use the Analyze Graph tools here, but I'm going to use the Geometry tool just to ensure that I've found all of the possible solutions. So we go Menu, Geometry, Points and Lines, and let's look for intersection points. Select both graphs, Escape to get rid of the tool, and the intersection point is the point 6 and 2.2. So definitely what I've done here is verified that my solution of these two equations is at the point where x is 6. I can move between windows by clicking on the tabs at the top of the calculator screen or control left arrow, control right. So there's our first question, completed. To start our second question, here we go. We're now solving for x. This is an exponential equation. I'm going to organize my document so that each question will be in a new problem. So let's insert a new problem. My first problem was question 1, so 1.1 and 1.2 refer to question 1. It's a good idea to do this because when you're in an exam situation and you'd like to go back and check the questions, if you have a new problem, a new tab open for each, if you open a new problem for each question, it's very easy to go back and find the questions that you'd like to check. So documents, I'm going to insert a problem. Again, in this case, I'm going to start with a calculator page. So I insert a calculator. And I'm going to use the numerical solve in the calculator application. So menu, algebra, and select numerical solve. Type the expression within the parentheses. So I have 2 to the power x minus 1, right arrow, multiplied by 4 to the power 2x plus 1. Right arrow is equal to 32. Again, in this equation, I'm solving for x. My variable is x, so comma and x. Enter. So it appears that my answer is 0.8. Now, maybe in this particular question, I'd like to express this as a fraction, not as a decimal fraction, as a proper fraction. So in order to do that, let's approximate that answer to a proper fraction. We can see it's 8 out of 10, but it won't always be easy to estimate or calculate what the fraction is. So menu, number, approximate to fraction, and it should give me the answer 4 thirds. There we go. Again, I'd like to verify this answer. So I'm going to also use a graph application and find the points of intersection of those two graphs. So control, doc, add a graphs application to this problem. So you'll see that I'm in 2.1 and 2.2. Both of these pages relate to question 2 on my exam. Right, so the first graph that I'm going to draw is the left-hand side of the equation, which will be 2 to the x minus 1, right arrow, times 4 to the 2x plus 1. So that's the first part of my first graph. I'm trying to find out where this graph intersects with the line y equals 32. So tab y equals 32. So my second graph is simply the line y equals 32. And it hasn't popped up. I wonder what's happened. Now this will happen often in a test where you type in a graph and the graph doesn't actually show. The most important thing is to just don't lose your cool. Think about what am I looking for. The line y equals 32 is clearly going to be quite a lot higher than the range that my window actually shows. So I'm going to have to increase this value to larger than 32. Let's make it 40. Oh, there's my graph. So now I can see both of my graphs quite clearly, and I'm trying to find the point of intersection of these two graphs. In this case, I'll use the Analyze Graph tools because there's clearly only one point of intersection. So menu, Analyze Graph, intersection, and simply slide over the the intersecting points. So that validates for me that the graphs intersect when x is 0.8. Control left arrow. That was the solution I found using numerical solve. So at this point, I'm pretty happy with what I'm doing on the test, and I've got both of the questions that I've done so far correct. Let's look at question 3. In this question, I need to sketch the graph of y equals 2 natural log of x minus 1. I need to label the x-intercepts and the asymptotes and state the implied domain of the function. So this is my third question. So I'm going to insert a new problem. So document, insert problem, and I'm going to be drawing some graphs. So I'll add a graphs page. So you'll see now I'm on question 3 and I've got a graphs page there. Well, let's have a little look at this graph and think about what the different elements of this graph are telling us. So y equals 2 natural log of x minus 1. Let's start by looking at the graph y equals natural log of x and see what that looks like. So you wouldn't necessarily need to do this in a test, but just to go back a little bit and see what the transformations of this graph look like, that's a useful exercise. So y equals natural log of x looks like that. So this graph appears to have the y-axis as an asymptote, and it appears as if the value of x is going to continue to increase to infinity. Let's add in another graph now. Let's look at what does the graph of 2 natural log of x look like. Yeah. So this graph, the red one, also has the y-axis as an asymptote, and the x value continues to infinity. Move the labels. Both of these graphs pass through the point 1, 0. The value in front of natural log appears to be a dilation in the y direction, which is a similar transformation that you will have discovered in all of the functions that you have looked at throughout the mathematical methods course. The graph that I actually need to look at is the graph of 2 natural log, so control natural log of x minus 1. So what's happened now with this black graph is it appears that the graph has shifted to the right. Again, that ties up with the transformations that you've done across the board, where it's shifted one place to the right, and it appears as if the vertical asymptote is now the line x equals 1. So we're looking at the black graph. We want to explore the black graph, so I'm going to switch off the other graphs, tab and up arrow. By deselecting the graph, we can switch off the other graphs. So now I'm looking just at the graph that I need to be investigating. I need to label the x-intercepts and the asymptotes. I've said from my equation it appears that the asymptote is the line x equals 1. Well, in order to draw that line on my graph, because that's not a function, I actually have to use the relation feature in the menu. So let's go menu, graph entry edit, relation. And the relation that I think, so I'm typing in what I think is the asymptote, is x is equal to 1. And it certainly appears that that is the asymptote. So there is my asymptote. So the graph is asymptotic at the line x equals 1. Let's look for the x-intercepts. X-intercept at that point there, I can see straight from the graph it appears to be 2. But let's just verify. So menu, analyze graph, 0. Remember the x-intercepts are called the zeros. The graph I'm looking for is the black graph, and slide the dotted line over the 0. In looking at this question, I can see that there won't actually be any y-intercepts. In some cases there will, and you would use the graph trace feature to find the y-intercept, but there's no y-intercepts here because the graph is asymptotic at x equals 1. The last thing I need to do is talk about the implied domain of the function. So the function appears to almost, as x decreases, my graph is approaching the line x equals 1. So x equals 1, in order to find the implied domain, I would be saying x is in between 1 and infinity. So x would be an element, and here I'd need to use my round brackets of 1, infinity, using round brackets around my domain. And that brings us to the end of question 3. Let's have a look at question 4. So for question 4, data was collected of the population of ants in a nest. Always interesting, the things we collect data on. So the population of ants in a nest, population is T, after T days. The results are shown in this table. Using technology, plot the graph of natural log of P against natural log of T. So this question is telling us what graphs to plot, and then which constants to find in order to find, it would appear, the growth expression, the exponential function that models that situation. So let's start a new problem. So doc, insert problem. Because I'm going to start with my table of values, I'm going to start by inserting or adding a lists and spreadsheets page. On my lists and spreadsheets page, I need to enter the data that I've been given. So my independent variable is time. So let's call this T. At the top of the column, type in T, enter. My values for time are 3 days, 5 days, 10 days, 15 days, and 20 days. My next column is the population of ants, so I'm going to call that P. After 3 days, there was 120 ants. After 5 days, there was 590 ants. After 10 days, there were 4,000 ants. After 15 days, I hope these weren't termites, there were 15,700 ants. And after 20 days, there were 38,100 ants, clearly an exponential function. Once I've inserted my values into the lists and spreadsheets page, I could draw that graph if I wanted, but in fact the question is asking me to plot the graph of natural log of P against natural log of T. So instead of plotting this graph, I could plot this graph on a scatter plot page, and that would show me quite nicely that it's an exponential function. But let's go straight into what the question's asking us to do. So we need to find the natural log of T and the natural log of P. So I'm going to type here, I'm going to call this column LNT, or natural log of T. In the function line, I'm going to put the function because I want to find the natural log of the variable T. So we'll type equals control natural log and T. Push return. The calculator asks me, is this a variable or a column reference? Well, it's the variable T, so I'm going to use variable reference, and it fills in the column for me. So that column is the column of the natural log of column A. Column D needs to be the natural log of the population of ants, so I'm going to call that LNP and do exactly the same thing. So I've got equals, control natural log, and it's the column with the variable reference of P. Again, it's a variable reference, and there's my list of values. So the graph I'd like to plot is the graph of natural log of T against natural log of P, so column C and column D. In order to do this, I'm going to use a scatter plot. Now, I could use the graphs page, but the reason I'm going to use a scatter plot is because it looks like in order to find the values of A and B, I'm going to need to do regression, and it's probably easier just to do the regression on the scatter plot page. So, control, doc, data and statistics. So on my x-axis, I'm going to put the natural log of t. On my y-axis, I'm going to put the natural log of p. Which gives me a linear function. At this point, I'm going to look at the regression. So menu, analyze regression, and I'm going to show linear regression. And in this case, I've found my y value, natural log of p is y. My x value is natural log of t. So I've found my value of A. A would be 3.01 and B would be 1.47. So the next part is really information that I'm going to have to work out probably on a piece of paper. So I found the value of A to be 3.01. Let's look at this on a notes page. So we found A is 3.01 and B is 1.47. Right, so my expression that I have found is the natural log, so ln of p is equal to A, which is 3.01, times ln t plus B, which is 1.47. So that's the expression that I have found from the graph that I've got. Now, hence find approximate values for constants A and B such that P is equal to B T to the A. So I need to look at my expression now and find a way of using my natural log expression to turn it into an exponential function. Right, there's a couple of ways I'm going to do this. Well, the way I'm going to do this, there's a couple of ways this can be done. The way I'm going to do this is to start by subtracting, so taking this equation, and I'm going to subtract so I've landed up, all I've done here is I've subtracted 3.01 log of t on the left-hand side of the equation. The next thing I'm going to do is use the rule or law of logs that says this number in front of the log can become the power of t. So that will give me the 3.01 becomes, let's see, to the power right, so my expression looks like this. The next law of logs that I'm looking at here is, oh, I could have just done this using a, yeah. When I subtract logs with the same base, I can divide the numbers, so that gives me ln p ln p over t over 3.01. Which is equal to 1.47. And rearranging this now in exponential form, my base is e. My power is 1.7, which equals my number. To solve for p, multiply both sides by 2 to the 3.01. Right, so here I've got multiplied by and this is now simply p. Evaluate e to the 1.47. We'll need a calculator page for that. We don't have one yet, so I'm going to insert a calculator page. I'm evaluating e to the 1.47, which gives me 4.35, rounding to 2 decimal places. So my expression becomes 4.35. Which means that the constant in my original expression b is equal to 4.35, and the exponent for my expression a is 3.01. So I can then say that a is equal to 3.01 and b is equal to 4.35. Further questions could have been asked in this instance to discuss the growth rate, the number of ants in the colony at a certain point in time, etc. I hope this has been useful. Thank you very much for joining us in our mathematical methods revision webinars. Join us again tomorrow in the morning. There'll be 2 webinars tomorrow morning, which I'm sure will be equally useful. I hope all your questions have been answered. Thank you very much for joining. Good afternoon.